Doubtful. All right, guys, so welcome to the Torch Talk today. I am talking about nuclear energy today. We're going to talk about basically nuclear power plants and how we get that energy, but then we're going to go back into history and look at two specific nuclear disasters, okay? I might have gone a little too technical, so I went back through and tried to ease up on some of that specific science behind it. So if it gets a little too much, just, I don't know, nod your head off and like pretend like you're sleeping or something, I don't know. But, all right, so nuclear power plants. The way that they work is through nuclear fission. And so what that means is that there is a uranium nucleus that's going to get hit by neutrons, and then that's going to decay, break apart into different elements. But I want you to keep in mind this bombarded with neutrons, because that's going to come back to our first nuclear disaster, so keep that in mind. But whenever it does get hit with those neutrons, it's going to release a huge amount of energy in the form of heat. It's going to come off with byproducts, and then it's also going to give off more neutrons. And then those new neutrons are going to hit new uranium nuclei, which then is going to create the process again. And so it keeps doing this until it reaches a self-sustaining nuclear reaction, okay? Yeah, so what's the PowerPoint's purpose? Obviously, it's to keep control of that nuclear energy that's happening, that chain reaction that's happening, and it's to regulate how much energy we're putting out as well. So yeah, there's our little note. Remember that for nuclear disaster 1, which will be, spoiler alert, it will be a man by the name of Louis Slotin, okay? So this is where we get a little deep into it. So let's just look at it from a big overview. So what are some of the byproducts that might come off of the uranium atoms? So we might get some barium, krypton, different isotopes, xenon, strontium, cesium-137. Hopefully my kids from Gen Chem 1 remember something significant that happened with cesium-137 at the beginning of this school year. The shrimp, yep, the radioactive shrimp at Walmart was cesium-137. So remember, that is a radioactive isotope, which again could then lead to prolonged exposure, could lead to radiation sickness, okay? And then iodine-131 as well. But then remember, we're gonna keep giving off more neutrons, and those new neutrons are gonna hit more uranium nuclei, okay? Now, it is possible that, this doesn't happen as often, but it is possible that the uranium nuclei won't split when it's hit with the neutron. It is possible for it to actually grab a hold of one of those neutrons and actually become heavier. But again, that doesn't happen quite as often. So this is just telling you if that uranium is just allowed to sit there, that waste, that nuclear waste, it will eventually decay into very harmless particles, but that's going to take a long time, depending on their half-life. So again, my kids, you should remember half-life. Also the higher or the longer the half-life, the less radioactive we consider it, okay? Because it's going to be very, very slow decay process that's occurring. So the 2 to 3 neutrons are released. Again, they're going to get absorbed up by, within a nuclear power plant, they're either going to get absorbed by what we call control rods, or they're going to hit more fuel pellets within the fuel rods to continue the reaction, or if they're absorbed by the control rods, it's going to slow down the reaction, okay? So within the nuclear power plant, how does, we're starting with the fuel source. Okay, so where do we find uranium? We find it in the Earth's crust, all all right? We find it in volcanic rock, sedimentary rock, granite, okay? Once we ore it, we get the ore out of the ground, mine it out of the ground, it has to go through a refinement process and an enrichment process, okay? So it's gonna go from uranium ore to yellow cake, to then it's gonna get heated up and changed into a gas. It's gonna get put through a gas centrifuge, which hopefully we know from maybe some of our biology classes, it's gonna spin really quickly. And so the two types of uranium that we're gonna find in the Earth's crust are uranium-238 and uranium-235. Now uranium-238 is the one that we're gonna find in so much abundance. It's actually 99.3%, I believe, is the amount of uranium-238. Now uranium-238 is still radioactive, but it is primarily only going to give off what we call alpha particles. Alpha particles are really easy to protect against. All you need is skin, okay? So our skin is the barrier that stops the alpha particles from getting inside. Alpha particles are dangerous though if you do ingest them or inhale them. So if they can get inside your body, that's where the damage is gonna happen. But outside damage, so just standing by it, it's not gonna really do anything. All right, you're not gonna reach any sort of lethal dose with it. But with the gas centrifuge, the heavier atoms, so the uranium-238, as it spins, those are gonna get pushed out to the outside of the centrifuge, and then the uranium-235, which is what we need, that is the fuel source, that's gonna be on the inside. And then it's gonna get pushed through these streams, and then we collect the uranium-235. Now again, I said uranium-238 is 99.7% of what we mine out of the ground. And so the remainder is the 0.7% that is uranium-235. So again, the 235 is the fuel source. So you can imagine we need a lot more than just 0.7 to actually get any amount of fuel. And so that's when it undergoes this process, which is the enrichment process. And that is where we need to enrich it to about 3 to 5% uranium-235. And again, that's going to be based off of the weight. The differences in the mass is what's going to allow us to enrich it to that 235, to the 235 amount that we need. Okay, difference between enriched uranium that's used for nuclear fuel sources versus weapons grade is the amount of uranium-235 there is. So for fuel, we need only 3 to 5%. For weapons grade uranium, we need something close to 90%. It might actually be a little bit higher than 90%. So just thinking about how much, if naturally occurring, you only have 0.7% uranium-235, you can imagine how difficult it is to get your hands on weapons grade uranium, okay? Which is a good thing. We like that, okay? Once it is enriched though to that 235 threshold that we need, it gets actually kind of put through like a kiln type thing where it gets heated up into these little pellets. The pellets are only like 1/2 inch high, and the diameter is about 1/2 inch, so they're pretty small. But then they get put into these fuel rods. Okay, so let me show you those. So through the enrichment process, it becomes uranium dioxide. That's what the ceramic pellets are made up of. And then you can see they get slid into the fuel rod itself. And so this whole fuel rod is made up of these uranium pellets that are ceramic. So these things are very, very heavy. It's not like a ceramic dish. It wouldn't be that type of weight. They're gonna be significantly heavy. And in order to get the fuel rod assembly, you need a ton of the fuel rods, okay? There we go. All right, so, yep, they're packed in, they're put into the metal tube. Just so you know, the metal tube itself is actually zirconium alloy. We use zirconium in order to not collect those neutrons that come out of it, because again, if we limit the amount of neutrons, we're not going to be able to sustain that chemical chain reaction, okay? So the zirconium will allow the chain reaction to continue. Okay, so we put a lot of fuel rods together to make the fuel assembly. And then, okay, the next slide will show you, we're gonna put those fuel assemblies then into the reactor. But this is just letting you know, a typical one weighs about 1,100 pounds, so it's very heavy. And those are gonna go inside the reactor. So this is just a diagram. I do have a picture of what a reactor looks like for real. But let's just look at the picture first. So you can see our the fuel assembly, okay, the fuel rods. And now in between those, there's gonna be spaces that we put control rods in, okay? And so this is just telling you we have that continuous danger or that possibility that a chain reaction could become uncontrolled, which would spark a meltdown, which is the exact opposite of what we want. So we use the control rods to limit how many neutrons are available to hit more uranium nuclei, okay? So those, the control rods are gonna be made up of specific materials that are going to absorb neutrons instead of reflecting them, okay? So boron, cadmium, things like that. You will also see, oh, yeah, here's, we call them neutron sponges because they're gonna soak up those neutrons. But you'll also see when we talk about safety protocols that now exist after the 80s and things that happened in the 80s, you'll see that one of the safety protocols that we now have is actually containment spray. And that spray actually has boron in it in order to, again, act as a neutron sponge to lessen any available neutrons. So to stop the reaction from occurring. Now, you can also see those control rods are kind of pulled out in that first picture, and then we slide them down based off of how much power we want to allow. Okay, so as we push them down into the fuel rods, it's gonna slow the reaction. As we pull them up, well, actually that's backwards, excuse me. Nowadays they're they're still on top. And that's also another safety feature that we'll talk about, because we want gravity to be able to pull down those control rods if something happens. So those control rods will automatically fall down without us keeping them up. Okay, so that's another new safety feature that wasn't really available back in the 80s when Chernobyl happened. Okay, so this fuel rod, or excuse me, the fuel assembly, this goes into a vessel, a pressurized vessel, and inside that you actually have water. And now I said it's pressurized. It's pressurized at high pressures in order to keep the water from boiling. So the water will get to really high temps, like 300 degrees. We all know that the boiling point of water is 100. Thank you, my chem kids. So 100 degrees Celsius, right? So these get up to like 300 degrees Celsius, but yet there's still water. And if you go to our gas laws and you think about our gas laws, that's we have to increase that pressure in order to keep it from boiling, okay? So we actually use water though for another reason too. We call it a moderator because those neutrons that are flying everywhere, they're actually moving way too fast for uranium to even catch it. So even like if it hit the uranium atom, it's going too fast and it won't necessarily actually get the impact from the neutron, creating the chain reaction. And so we use water to actually slow down those neutrons and allow them time to actually hit the uranium atom, therefore causing the fission. okay? So that cooling liquid inside, multiple reasons why we're using that. And obviously it's designed to contain the fission process that's occurring. Now this whole vessel, so we talked about what was inside of it, then we have this vessel, and now that's gonna go into a larger containment vessel as well. Okay, so this one over here, this is our inside a reactor that's being worked on. It's not the blue light. The blue light has nothing to do with radiation or anything like that. It's the lights that are in there so that they can work. But you can kind of see the fuel rods down inside of it, okay? Over on your right, you have basically the diagram of how a nuclear power plant works. So we have two separate sets of water. We have the initial water that's inside the reactor itself, that is the one that's being super pressurized and staying as liquid water. And that's gonna travel through, let me make this larger. Okay, so this water that's in here, it's going to heat up and it's gonna travel through the pipes that are available to it. And so then, notice though that that's a closed system, so it's just gonna keep going through that same cycle. Whereas then it goes into another tank of water that has more water that's going to then be heated up by those hot pipes. And because that one's not pressurized, that water is allowed to go into steam, which will then again travel. This is all of our chemistry stuff, right guys? It's going to travel and take the shape of the container that it is in, right? So it's gonna travel over to the steam turbine, which is actually where we get the generation of the electricity. And then it's gonna get cooled off through another piping system that has cold water being pumped through it. And so then it's going to travel through it. And again, that's the only space or the only route that it's allowed to take as well. So the water that is coming into contact with the radioactive material that's in the reactor is not the same as the evaporation that you see outside of a nuclear power plant, okay? So you don't have to worry about any byproducts coming out of that. That is the secondary set of water, okay? And it's just a cycle. It just keeps going and going and going. All right, so the reactor pressure vessel, that's what we were talking about. More specifically though, I do this all the time, guys. I say what's on my slides before I get to them and then it pops up on my slides. So again, the coolant water is under that immense pressure so that it's not allowed to vaporize. And it's gonna be at really, really high temperatures, 300 degrees Celsius, but it's not going to boil, okay? Something pretty interesting. So the containment vessels, they are, have to, usually we create them to last somewhere between 40 and 80 years. But obviously not every single one is going to be designed exactly the same, and so there's gonna be differences between them. So we do need ways to just double check that those seals are actually still good. So one thing that we do is we actually put in like a steel, like a form of steel into the pressurized vessel itself. And then every so often it's shut down, okay, allowed to cool in. We remove those steel pellets and then we test those to see how brittle it has become. And then we make the determination, okay, this reactor is too brittle at this point, so then it gets decommissioned. Or you say, okay, this is not, it's not too brittle, it's fine, it's working perfectly, and it continues on. But the reactors get checked constantly. There's not a lot is left up to chance anymore. We have regular checks that go through by not just the people that work for the company of the power plant, but also government watchdogs as well. So FYI, they make bank. If you ever want a job. They make bank though because your life expectancy is not as long as normal, okay? So, yeah. I actually had a friend from high school who did it. Very rich, very, very rich, but okay. So what happens afterwards? What happens, we hear that nuclear power is one of the cleanest forms of power. Why is it the cleanest? And then don't we still have all this waste that's occurred? Yes, we do, okay? So part of all of that nuclear waste is still gonna be contained within those fuel rods. And so whenever the fuel rod is used up, we remove those. Again, remember they're really, really heavy. We remove those and we actually put them into fuel pools, okay? And they have to stay in that pool for about 5 years, because when it first comes out, it's gonna be really, really hot, and not a type of hot that you can cool off with just spraying some water on it and letting it sit for an hour. It's gonna stay hot for quite a long time because it's still undergoing radioactive decay. All right, so that's still gonna be giving off heat for quite a while. So those fuel rods get put into these pools for at least 5 years. Lengthwise, they're about 20 feet deep. Then they're shielded in order to, again, not allow any byproducts to escape from it. So then how do we typically get rid of nuclear waste? It has to get put into sealed caskets, and then we have specific storage sites. Most of them are pretty hidden and highly protected, because again, there's nuclear waste there that in theory could be recycled into something else, into a different use. So they typically are very protected. Had a cousin that protected one of those. So anyway, we take those fuel rods, once they cool off enough, we take those fuel rods, put them into the caskets, and then they get shipped to the disposal sites, okay? So that's the basic premise of how the power plants work. But we didn't start in this nice, I mentioned a couple of safety features that we have. We did not always have these safety features. In fact, we didn't even have safety features for our own personal interaction with radioactive materials at first, because we didn't know, right? We all know about Marie Curie. Please shake your head yes. Just, even if you don't know, just pretend and shake your head yes. Okay, all right. So we know that Marie Curie died from, well, her official death certificate does not say acute radiation sickness. I believe it was aplastic anemia, maybe, was what her official death diagnosis was, but she carried around polonium, radon. Yes. And she liked it. She would carry it around because it glowed, and so she liked the color that it gave off, and so she always carried a little vial around with her, not knowing that it was actually making her sick. So to this day, we're not really able to go through her notes. Her notes are kept in lead-lined boxes, and if someone needs to go through them for some reason, they have to go through the whole safety protocol of the full hazmat suit, all of that stuff, and they have to get special permission to go in to actually take her notes out of the lead-lined boxes. FYI, her daughter also died of the same thing. So we're going to talk about that now. So what are some of these nuclear disasters that we've dealt with throughout history? So to the left, we have a sign surrounding Chernobyl, the area of Chernobyl and or Pripyat, which is the city that was built for the workers of the power plant Chernobyl. And obviously this is Russian, or Ukrainian, excuse me, but radioactive, it does mean radioactive. So 2 nuclear incidents that we're going to discuss. Louis Slotin, which was 1946, right at the end of World War II, and then Chernobyl. All right. So first off, Louis. All right. So Louis Slotin, he was a Canadian physicist. I think Winnipeg, if I remember properly. He was a part of the Manhattan Project from beginning to end, so 1942 to 46. Keep in mind too, not all of the Manhattan Project occurred in Manhattan, right? We know that. There were actually 3 different sites that we used. One in Tennessee, one in New Mexico, and one in Washington. The third one was Washington. So different things happened at the different sites. So in 1944 though, Slaughton was actually moved to Los Alamos, excuse me, which is, Los Alamos was the site where we actually created and assembled the weapons that we used for the nuclear bombs, okay? So what is he known for? He is famous for being the one that assembled the plutonium core for the Trinity test. The Trinity test is when we actually, it was our first true nuclear weapon test. And so he was the one that actually put it together. After that, he became known as the Chief Armorer of the United States. That took place, the Trinity test took place in July, I think I have it in my notes. So they started the assembly on July 12th, and then it wasn't finished until July 15th, 1945. And so at that Trinity site, we have lots of famous scientists, including obviously Slaughton, Oppenheimer, okay? And then another one that I remember because we talk about him, all my chem kids should remember, James Chadwick, okay? So he is also on site. There's plenty of other really important scientists there as well though, but those are 3 that I would point out, okay? So the test took place the morning of July 16th, and they say that once it was at 5:30 a.m., and that was when the nuclear age began. But also at Los Alamos, that's where we created 3 plutonium cores for the weapons. Now the 3, okay, Gadget was first. That was for Trinity. That is the fireball that came off of Gadget, when Gadget went off. One of the scientists too, again, remember we didn't know a lot about safety protocols at this time. They did, for safety reasons, they did separate the scientists and they put them at different sites in order to protect them if something went wrong. I'll also tell you, no one imagined that it would ever be as big of a blast as what it was. They thought that it was gonna be way less than what it was, but it was not. But yes, so Gadget was first. That's the first one that we tested. Then we made Fat Man, which was the core that was used when we dropped Fat Man on Nagasaki. And then the Demon Core. It was not originally named Demon Core, that came along later on. But the Demon Core was actually intended for a 3rd bomb that we never dropped. Because Japan actually surrendered, so we didn't have to use that 3rd bomb. Now, notice there's one missing, right? Okay, Little Boy is missing. So Little Boy was actually completely different. Little Boy was actually uranium, and again, it went off on Hiroshima, okay? We only had enough weapons-grade uranium for 1 bomb. So we never actually tested Little Boy before we used it. The test was dropping it on Hiroshima, okay? Quick side note too, obviously we're previewing Chernobyl, but Hiroshima and Nagasaki, can people live there? People can live in the 2 Japanese cities. So Hiroshima, Nagasaki. I'm actually going to Hiroshima in about a month. I'm super excited, super nerdy of me, but yes, I am going there. I won't get to Nagasaki, but both of them are thriving cities, no residual radiation. It's perfectly fine to live there. Chernobyl, people live there, yes. It is technically illegal to live there though, but there are staffers that work consistently at the site, and some of the more stubborn people that lived there originally moved back a few decades after Chernobyl happened. So what's the difference between the two? Like why with two nuclear bombs can we live there but not with a nuclear meltdown? The difference is where the bombs went off. So Little Man and Fat Boy, sorry, Fat Man and Little Boy, excuse that, they did not hit the ground before they exploded. Okay, so they exploded in the atmosphere, which actually allowed, now it allowed for maximum blast impact, so a lot of immediate damage occurred, but long-term wise, the radiation didn't really settle into the soil, and so because of that difference, whereas Chernobyl was on the ground and everything got blasted into that general vicinity, that soil is still radioactive. Whereas Nagasaki, Hiroshima, they escaped the long-term lasting effects of the radiation. Okay, Nagasaki is actually, that was actually bigger, significantly bigger. I want to say Hiroshima or Little Boy was 15 kilograms or kilotons, excuse me, not grams, kilotons, of the equivalent of 15 kilotons of TNT, whereas I want to say Fat Man was like 30 kilotons, okay? But Hiroshima actually got more damage than Nagasaki, and that's because Nagasaki, it was up higher, but then they were also mountain, like they're very mountainous in that area, and so a lot of the blast was contained within that valley, and so widespread Nagasaki was actually spared a lot because the blast was contained to within the valley. Whereas Hiroshima, that blast was allowed to travel a lot farther, okay? So just some World War II history put into there for extra. Okay, so again, Little Boy, which was dropped in Hiroshima, uranium, not plutonium, and was never fully tested. All right, so Louis Slotin though, on May 21st, 1946, that is when his accident occurred. The name of the experiment that he was conducting is nicknamed Tickling the Dragon's Tail. He died on May 30th, 9 days after his accident. He died from acute radiation syndrome or sickness. Some people say syndrome or sickness. And that was at the age of 35. So, all right, what is tickling the dragon's tail? Well, I'm glad you asked. Okay. So, the tickling the dragon's tail was a experiment to determine how much or how many neutrons we need in that reflection, reflecting that, bombarding the uranium in order to, the plutonium, in order to get, to reach criticality. So criticality is when we have enough of the uranium being bombarded that a self-sustaining chain reaction, it can then occur, okay? So we no longer have to continue to help the neutrons move around or by reflecting them. It has enough reflection that it will sustain itself on its own, okay? So what they were doing was they were seeing how much, there's two accidents that happened with the Demon Core. The first one was with Harry Doglin. He used tungsten carbide bricks. So that's what he was using in order to reflect the neutrons. Slotin was using beryllium spheres, half spheres. Okay, so they were two different reflectors occurring. And remember I said, remember that neutron bombardment that we were talking about on that first slide? So that's what's happening here. We're bombarding the plutonium core with more neutrons to again escalate that chain reaction, So yeah, Slotin used beryllium. Okay, so screwdriver. It's a strange note there, but it's important. So typically, a safety protocol in place at the time was that they used these like clips, and you can actually see it right here. It slid into place in order to ensure that the two barium spheres would not completely touch. If they completely touched, criticality would be reached, and that's what we did not want. So what Slotin did though, Slotin was known as kind of an adrenaline junkie. You can see different pictures of him being like super close to radioactive things without any protective gear, and a little cowboyish. Okay, so he believed that using his own instincts, he would be safe enough to do this experiment. And instead of having those blocks in place to protect himself, he would put a screwdriver inside. And now there was a thumb holder for him at the top. You can see his thumb is in that. So he would hold the top, and then he would put the screwdriver so that the thick part of it was separating it. And then in order to test the criticality, he would turn it in order to allow it to get closer to each other, to see how much, until he reached criticality. Okay, so Fermi, he was actually quoted as telling Louis Slotin that if you keep doing that experiment that way, you'll be dead within a year. And he was correct. Okay. So the accident, it occurred May 21st, 1946. This is Slotin's last day before retirement from Los Alamos. He is moving on. So he is actually taking his replacement on a tour of Los Alamos. This is also the last day of the Demon Corps' existence. The following day, it is supposed to be melted back down and returned to our weapons stockpile, okay? Last days, right? That's the day when it happens, yes? All right, so Slotin and 7 other scientists, including the guy that's supposed to take over his position, touring, he says, hey, let me show you this experiment. It wasn't scheduled, nothing. He was just gonna show it to him. Because he'd done this experiment a ton of times. No issues before. So he has that screwdriver in. The diagram is showing you how far each scientist was away from the core. There is one scientist, it doesn't really portray it 100% here. There is one scientist who's like halfway behind Slotin, so he does receive pretty much a lethal dose of radiation, but a lot of it is blocked by Slotin. But the 7 scientists are spread out around the room, and he's using his screwdriver without the clips in place, and his screwdriver slips. And the beryllium half sphere on top falls into place. And at that moment, they said that they saw a blue light emerge from the core, and they felt an intense heat wave go through them as well. And so Slotin, as fast as he possibly could, if you remember his thumb is still here, he picks up the beryllium shield and tries to pull it off as fast as he possibly can. But it doesn't matter. In those microseconds, they still receive he receives a lethal dose of radiation. So it's estimated that he received 1,000 rads. He was also not wearing his badge. So they still had badges back then, like we do for medical personnel that are using the X-ray techs or anyone working in a nuclear reactor. We still have those. They had those badges. Then that could actually test how much radiation they had been exposed to. No one was wearing them. They were all in a box. And so one symptom of this much radiation is mental confusion. And so Slotin actually told one of the scientists to go and grab their badge, the badges, and then they placed them where each scientist was, so that then they would be able to go back and actually measure out how much radiation they believed they were hit with. That also put that scientist, though, in more danger of getting more radiation. But again, they believe that because of the mental confusion, Slotin wasn't thinking quite straight enough to realize that he was putting his friend into more danger. So once they took the diagram of where everyone was standing, they exited. And Slotin is said to have started puking as soon as he came outside, starting with a symptom right away. And once he pulled off the beryllium sphere, he's quoted as saying, "Well, that does it," meaning he knew in that moment that he had received a lethal dose of radiation and his life was on a clock at that point. So his symptoms, immediate nausea, shown by the fact that he went outside and had to puke right away. Different medical professionals also obviously went in and was treating him as much as they possibly could, but they described it as a 3D burn internally, and also to his hands, because his hand was so close to the core. So that sunburn, just like outside sunburn, you can imagine how much pain that would be. Severe gastrointestinal failure, the mental confusion, and then really quick, well, not super quickly, he actually, when he underwent this burst of the radiation, he had these initial symptoms, and then they cleared up for a little bit, but then within a week, it was back and it was worse, and he was again being treated just to keep him comfortable. So the swelling of the hands is a big thing. He did donate his body to science to allow scientists to see the effects of that amount of radiation. And so, like, basically his entire, the entire process of him dying from the radiation was caught on film. Scientists were taking notes, like keeping track of the symptoms, observations for scientific reasoning. So one of the big things that got caught on film was actually his hands. I do have pictures of those, but I just didn't feel comfortable putting them up here. They are gruesome, pretty gruesome. They swelled, but then they blistered, and then they even started to look deformed. So it is pretty hard to watch. High fevers. Then he went into a coma, which was followed by his death 9 days after the incident occurred. Because Los Alamos was an army base, the U.S. Army did call in his family. They paid for his family to come down, and so his family was able to be with him in those last few days. So he did have the comfort of family with him. But Louis Slotin is considered to be the person that has received the most radiation of anyone ever, because after Slotin, a lot of safety protocols got put into place after Slotin. So Harry Doglin was before. I want to say he was about 7 months before Slotin, and then Slotin. So then with the second accident of the Demon Core, that's where the safety protocols came into place. The core was melted down and was returned to the stockpile, okay? So that was Louis Slotin. Next we have Chernobyl, all right? So in 10 days, it will be the 40th anniversary of the Chernobyl meltdown, okay, April 26, 1986. You can see the reactor 4, this is reactor 4 here. And then I also want to show you this map too, so that you can kind of picture where it is. So keep in mind 1986 is, it's not Ukraine, it's the USSR. But it is in modern day Ukraine. I don't even like saying modern day because it's still like modern, but today, what is known as Ukraine. So Kiev is right about, is there, Kiev being the capital city of Ukraine, and then Chernobyl was about 2 hours north of Kiev. So when we get to the evacuation, a lot of the evacuated people actually were sent to Kiev. So again, remember, you gotta set the stage. This is the height, well, actually I wouldn't say it's the height of the Cold War. This is the final coffin, or the final nail in the coffin of the Cold War and of the Soviet Union. So Gorbachev actually said that he thought that Chernobyl was the real cause of the fall of the Soviet Union. And that's for a couple of different reasons. Mostly because of the cost of trying to contain the fallout. It was a blow to a system that was already on its last leg. It was also an issue because Chernobyl caused a lot of distrust in the Soviet government, because prior to Chernobyl, the Soviet Union was very, very hush-hush about everything. There was no transparency with the people of the USSR. And so after Chernobyl got out and everyone found out about it, it kind of pushed a lot more people into fighting against the government, which again is another reason for the fall of the Soviet Union. So it was reactor number 4 that had the meltdown. And why did it melt down? Okay, great question. So from the start, the Soviet design of the power plants had 2 major flaws. And both are okay, I'll just share them both with you. So the first one was it had a positive void coefficient. So in our reactors, well, almost every Western reactor, whenever we put water into the reactor, it slows down the reaction. It was the exact opposite with the Russian reactor. And I don't know why, I don't know what was that cause as to why it actually sped up the reaction. Everything just says it's part of the design. And so that specific reactor is the RBMK-1000. I cannot tell you what the RBMK stands for because it's all Russian or Ukrainian Russian words, I'm not sure which one. I would assume Russian words. But the steam sped up the reaction, which was no good. We did not want that. So then it created this feedback of more heat gave you more steam, which gave you more power, which gave you more heat, right? Instead of doing the opposite and slowing it down. The second issue was that the tips of the control rods they were actually made up of graphite, so carbon. And so when what was called the scram button, when the scram button was hit, the first part that went into the fuel rods was this graphite. And so that graphite actually caused the reaction to speed up extremely fast, even in those seconds, just a few seconds of traveling down into where then it would finally get to the control rods, right? Just that little initial tip of it sped up the reaction to the point where it was too much, and it kind of acted, I think I put it on here as it acted as a detonator. So as soon as those graphite tips hit down into the fuel rods, it exploded. Then the other big issue with that reactor was that because it was so tall, there was no containment building. Big issue, right? If something goes wrong, we need to contain the fallout. And so that type of reactor did not have a containment building. All right, so what goes on? The night of the 26th, the night shift is running an experiment to see if there's a blackout, if the turbines would still power the cooling pumps. Okay, now, issues with that though. The test was actually delayed by 10 hours because of an electricity grid issue, where there wasn't enough electricity to actually run the test during the day. So they had to wait until nighttime when they could get an excess of electricity to actually run the test. So that meant that the night crew was running the test instead of the day crew. The night crew had never been fully briefed on what the experiment was. So that's one issue. Your scientists need to know what they're doing, yes? And then because it had been delayed for so long, there was a buildup of xenon-135 inside the reactor, which we actually sometimes call radiation, or excuse me, nuclear poisoning within the reactor system. And so they couldn't keep the power to the levels that it needed to be at. And so to compensate for that, they actually basically removed all of the control rods. So you see this sequence of events that's happening that sets up the perfect storm for a meltdown. Okay, so the night of the disaster. It occurs at 1:23 a.m. at 4 seconds. The test begins. The turbine valves are closed. And again, instead of shutting down and cooling off, the power goes up. And that's not what's supposed to happen. It's supposed to start going down. So by 40 seconds, they know that something is wrong. Something is not working the way that it's supposed to work. So the senior operator hits the emergency shutdown, which is called a scram button. He hits it, and then again, what did I tell you about the graphite? So the graphite enters into the fuel rods, and then it actually causes the explosion. So instead of stopping, the reactor power spikes over 100 times its normal capacity, and then you get 2 explosions. So the first one is the steam explosion that's within the pressurized vessel. This is enough energy that it actually blows the top of the reactor and the roof off of the building. So then it has a straight shot to the atmosphere, okay? All of that nuclear waste or byproducts. The first firefighters are on the scene 4 minutes later. Well, technically like 3 minutes later. It was 1:23, sorry, 4 minutes later. So the first firefighters are on the scene at 1:28. They were not told though that it was radiation, that it was part of the reactor that they were fighting the fires for. So all of these firefighters went into this straight next to pure radiation to try to start putting out the fires. Those fires go on for about 2 weeks. Specifically 9 days, but then there were still some other intermittent fires that occurred up to 2 weeks later. Now, you would think that the normal thing to do would be to get everyone away from the site, yes? Soviet Union decided to keep it quiet and not tell anyone what happened. Unfortunately, that means that all of those people that lived in what we call the exclusion zone, which is like a 19-mile radius around the reactor, that means that all of these people were being exposed to these high levels of radiation for 36 hours after the explosion occurred. So after 36 hours, I never remember the statistics here. So the city of Pripyat had about 50,000 people that were evacuated. It took 3.5 hours, and they used 1,200 buses to get everyone out. And Pripyat is less than 2 miles from the reactor, so it's really, really close. Remember, that's the city that was built specifically for the workers of the plant and their families. So we have supermarkets there, we have schools there, we have hospitals there, we have everything there. All right, so they go in, they get everyone out, they tell everyone to come to the buses, leave everything, don't take anything. You're only gonna be gone like 3 or 4 days, so don't worry about your stuff. Get on the buses, come with us. They get transported to Kiev, where they remain, basically most of them forever, okay? No one is ever really able to return. I know, guys, I'm getting short on time. Okay, so after that though, we had a lot of looters come through Pripyat, and they would actually steal money and jewels and things and sell it on the black market. And so we actually got, people would get radiation poisoning around the world from those that had bought or stolen those items because they were keeping those items in their possession and they were radioactive, okay? So the other places that got evacuated was the city of Chernobyl, which is like 9 to 10 miles away from the power plant. And then you had a lot of smaller villages. So around 115,000 to, some estimates say all the way up to 315,000 people did end up getting evacuated. So what all was affected? So the exclusion zone was the 19-mile radius around the power plant. Sweden is actually the first to know outside of the USSR that the meltdown occurred. The way that they found out, the Forsmark nuclear plant Their scientists were walking into through their sensors to get to their job at their power plant, and all of a sudden the radiation detectors started going off. And that's not supposed to happen. It's supposed to be when you come out of the detectors is when those scientists would get dinged. Well, what they realized was that they were trapping in the radiation on the bottom of their shoes. And so that's how it got out that something had happened in the USSR and there was an explosion, nuclear fallout there. And so there, at that point, the USSR can no longer keep it quiet. Belarus, also part of the USSR at the time, actually 70% of the fallout actually landed on Belarus. They still have a lot of health issues to this day. We got radiation was found in the UK, Italy, Greece. It's also found globally. Here in the US, we had traces of radioactive cesium, iodine was found here in the States and Canada, and then it also went to China and Japan. So it spread really, really far because anything that got into that atmosphere could move basically anywhere in the world. I'm running out of time, guys. Okay, so these are, remember that, so I was talking about ARS a lot, so acute radiation syndrome. Chernobyl actually released high intensity ionizing radiation. The non-ionizing radiation is like our typical like electromagnetic spectrum radiation, so like infrared and microwave, stuff like that. The ionizing one would be our alpha, beta particles, and then gamma rays as well, okay? Out of those three, gamma is the most dangerous just with us being there. The alpha and beta particles we're pretty much safe from with our skin as a barrier, but the gamma rays we're not safe from. And then there are the symptoms of radiation sickness are very similar to everything that Louis Slotin experienced. Okay, so death-wise, I'll stop here with it. Okay, 2 workers were killed in the initial explosion. 28 firemen died, and the cleanup workers died right in the aftermath. Most reports say within like 2 weeks of it, but safely we give it 3 months. Estimates were that 6,000 or more of the 600,000 cleanup workers, which was mostly USSR soldiers, died due to illnesses caused by the radiation. 5,000 thyroid cancers in the aftermath. The Ukrainian National Commission for Radiation Protection suggested figures as high as 500,000 total fatalities. That cannot be confirmed, especially because of the cover-up, but that is their suggested figure. Belarus, Russia, Ukraine still has issues with radiation. And then in 2005, the UN actually put out a report that they were expecting at least another 4,000 deaths still stemming from 1986. So, okay, I'm sorry, I went long. We have more stuff, but. Do you guys have any questions? I know if you guys have to leave, I understand. Okay, so feel free. But any questions? Yeah.
So I heard there's some people who are like paranoid when it comes to using Wi-Fi, Bluetooth devices. Do you think like if you like use headphones a lot or Bluetooth devices that you can have some form of exposure to radiation?
I say everything in moderation. I don't want you to live with those things on your head all the time. I don't think that there's any true scientifically accepted sources that say that it definitely causes it. It's more theory-based right now. So I think if it's true, we'll start figuring it out pretty soon because people have been using it for quite a few decades now. Yeah. Mine is up top. Make sure that you sign in for mine.
It was getting passed around apparently.
Is it this one?
Sure.
those of you that are hanging out, do you want to see some pictures from Capria?
I wanted to ask questions.
I wanted to ask
Or
a
question,
question.
okay,
too.
question.
Go ahead, Madeline.
Okay. This isn't exactly related to the nuclear aspect, but the cooling aspect of
Okay.
like the entirety, like the buildings.
The power plant.
Yeah, that. I can't think. So that reminds me of like what they used to use instead of air conditioning, and I think George Jenkins still used it for several years after like air conditioning was pretty
water cooling
popularized.
system?
Yeah, the water cooling
Mhm.
systems.
Yeah.
Is that similar or?
I would say that the principle of the piping is very, very similar.
All right.
Yeah.
I was just wondering.
Yeah. Yeah. Who?
You said that they had the experiment. It was in,
Oh, great question.
um,
So the night crew, why did the night crew push through and do it?
yeah, why couldn't they respond to the morning?
Because once the morning came about again, all the electricity in the grid would boost back up, and they would again fall short of the electricity needs. So what they should have done was waited, briefed the night crew, and then did the experiment. That was where their mistake was. Yeah. Oh.
Are we in
Yeah,
y'all's
I'm
way?
gonna Show you these pictures really fast, but yeah. What's up?
So the people in the
Yellow?
room when he had to like 911 the radioactive emergency.
Uh-huh.
If he stayed in the
Get out
room, would
of
the
here.
side effects been different than if he left the room?
No, for the
Do
most
we
part,
need
as
to
soon
leave?
as the blast went through and he pulled it off and stopped it,
I
it
don't
went
understand.
down very quickly.
Right
Now,
now?
there still could have been radioactive, the issue was where that touching things in the room would still give off radiation.
We have to go. Apparently they have a ceremony